In this lecture, we shall study moment of inertia for few objects with different geometrical shapes. We consider four types of different geometrical shapes. First one is the moment of inertia of and radius of gyration of a thin uniform rod. Okay, let us draw the rod. Suppose this is AB, and let O be the middle point of the rod, and we have an axis which passes through the middle point of the rod and perpendicular to its length. Let this axis let the axis is PQ. We consider a small element of the rod at a distance x from the origin of the middle point O, and the width of this element is dx. Let capital M be the mass of the rod. Then the mass per unit length. Let us call it lambda, and total mass divided by total length. And the mass of the small element with width dx. This dm equal to lambda into dx, because lambda is the mass per unit length and the length of the element is dx. So the moment of inertia for this small element of mass dm about the axis pq, our axis is pq, which is perpendicular to the length of the rod AB. So if you call this moment of inertia di, then it will be distance from the axis is x, so is distance square into mass. This is the formula for moment of inertia. And if you substitute the value of dm from here, okay, now if we integrate this over the whole length of the rod, we get the total moment of inertia. And we have to integrate from if we say the middle point of the rod is O, which is the origin, and so the left end of the rod will be minus L by 2 and the right end of the rod will be plus L by 2. So the limits of the integration will be minus L by 2 to plus L by 2 and di equal to this m divided by L x squared dx. So we bring the constants outside the integral sign, and this will be x cubed by 3 . So it will be L cubed by 8 plus L cubed by 8. So this is the moment of inertia of the rod about an axis passing through the middle point of the rod and perpendicular of its length. If the radius of gyration is k, then the moment of inertia is radius of gyration. uh, Sorry, the moment of inertia is mass into square of the radius of gyration. So equating 1 and 2. From which we obtain radius of gyration equal to L divided by square root of 12. Okay, so this is the radius of gyration of the rod, and this is the moment of inertia of the rod about an axis perpendicular to its length, passing through its middle point. Next, we consider moment of inertia and radius of gyration of a circular disc about an axis perpendicular to its plane, passing through the center. So if we have the circular disc like this and its center say at O, and this is the axis about which we are going to find the moment of inertia of the circular disc. So this is PQ. Okay, let the radius of the circular disc is small r, and we consider a ring at a distance small x, and the width of the ring is this small ds. Let capital M be the mass of the circular disc. Let sigma be the mass per unit area of the circular disc. Since mass of the disc is capital M and the area is pi r square, so the mass the ring with width dx is this, because sigma is the mass per unit area, and the area of the ring is this. Twice pi x is the circumference, this circumference, and dx is the width. So x twice pi x into dx is the area of this ring. Now the moment of inertia of this ring about the axis PQ it is x squared dm. So substitute the value of dm, it is twice pi sigma x dx, which can be written as twice pi sigma x cube dx. If we substitute the value of sigma, then it is capital M divided by par square. R is, you see this one. Now the moment of inertia of the whole disk about the axis PQ will be obtained by integrating this di. We integrate di, and the limit will be 0 to small r, and this is twice m, this is di equal to this, so it's twice m divided by r square, and this is x cube dx. So taking the constants outside the integral sign, so this one will be mr square by 2. if capital K be the radius of gyration, then I equal to K square. So equating this one and this one, we have okay, so this is the radius of gyration capital K, and this is the moment of inertia I for a circular disc about an axis perpendicular to the disc passing through its center. Okay, there are two other objects for which the moment of inertia and radius of gyration have to be obtained, but we have not considered so far, and these are for a thin uniform rod, but the axis should be at one end of the rod, passing through one end of the rod and perpendicular to the length of the rod, and the other one, the moment of inertia and radius of gyration of a solid cylinder about its own axis. We are not going to consider these two objects here. You can find the solutions, that means the how to find the moment of inertia and radius of gyration of these objects. You can find them from my notes that were uploaded in your Google Classroom. Okay, we shall now consider theorems regarding moment of inertia. There are two theorems. Perpendicular axis theorem and the second one is parallel axis theorem. Let us consider first the perpendicular axis theorem. Okay, this theorem says that the sum of the moments of inertia of a plane lamina about two mutually perpendicular axes in the plane of the lamina is equal to the moment of inertia about an axis perpendicular to the plane of the lamina and passing through the point of intersection of the two axes. If we have the lamina, say like this, Okay, let us consider that this is the plane lamina and O is its center of mass. Let OX and OY are two mutually perpendicular axes on the plane lamina. If IX and IY are the moments of inertia about the axis OX and OY respectively, then the sum of the moments of inertia IX plus IY will be equal to the moment of inertia IZ. This is the statement of the perpendicular axis theorem. Again, if I state the theorem, you will understand it. The sum of the moments of inertia of a plane lamina about two mutually perpendicular axes in the plane of the lamina is equal to the moment of inertia about an axis perpendicular to the plane of the lamina and passing through the point of intersection of the two axes. That means we have the two mutually perpendicular axes OX and OY. So the sum of the moments of inertia about these two axes is equal to the moment of inertia of the third axis, which is perpendicular to the plane of the lamina and passing through the point of intersection of the two axes. Okay, we are going to prove this. Let two mutually perpendicular axes OX and OY that we have drawn here, OX and OY on a thin plane lamina intersect at point O. The OZ, this OZ axis drawn at the point of intersection O and is perpendicular to the plane lamina. Let the mass of a particle at point P is at point on the lamina be small m. The perpendicular distances of the point P from the axes OX, OY and OZ are respectively x, y, z. I have shown here x, y, z. This is x is the perpendicular distance. This is the from the axis OY, and y is the perpendicular distance of the point P from the axis OX, and OZ the Z is the perpendicular distance of the point P from the axis OZ. So from Pythagoras theorem we have x square plus y square equal to z square. Yeah, from this triangle, this is x, this is x, this is y, and this is z. Because this angle is 90 degree. Okay, similar to the to the mass that we have considered here m, we can consider that the whole lamina consists of several number of particles of masses m1, m2, m3, etc., and their perpendicular distances from the OY axis are respectively as x1, x2, x3, etc. from the axis OX. Their perpendicular distances are respectively as y1, y2, y3, etc. from the OZ axis their perpendicular distances are z1, z2, z3, etc. So the moment of inertia of the lamina about the OZ axis is So we'll have to integrate over all the particles constituting the lamina. This is mjzj square, which can be written as now what we see from this is nothing but IA y, and this is IX. Thus we get IX plus IY equal to IZ. Proved. I hope that you have understood it. If you study the note, it will be clear to you. Very simple. Okay, next we consider parallel axis theorem. The statement is the moment of inertia of an object about any axis is equal to the sum of the moment of inertia of the object about an axis parallel to that axis and passing through the center of mass of the object, and the multiplication of the mass of the object and square of the perpendicular distance between the two axes. So if we draw the object like this, and we consider this is AB axis and another is CD axis. Okay, let the moment of inertia of an object of mass m, say the object of mass m, about an axis AB passing through the center of mass capital G, say this is the center of mass of the object. So if Ig is the moment of inertia, of the object about the axis AB, AB passes through the center of mass. Point G is the center of mass of the object. And let this distance between these two axes is h, and we consider a particle m at a distance x from the axis AB. Then according to this theorem, we will have I is the moment of inertia of the object about the axis CD. So according to this theorem, this I should be equal to Ig plus m h square, but m is the mass of the object and h is the distance between the two axes. We'll have to prove this. This is the parallel axis theorem. If I state the theorem again, then the statement is the moment of inertia of an object about an axis is equal to the sum of the moment of inertia of the object about an axis parallel to that axis and passing through the center of mass of the object, and the multiplication of the mass of the object and square of the perpendicular distance between the two axes. So let an axis, now the proof. We can consider that the object consists of several masses m1, m2, m3, etc., and the perpendicular distances of these particles from the axis AB are x1, x2, x3, etc. Then the perpendicular distances from the axis CD are respectively as x1 plus h, x2 plus h, x3 plus h, like this. So the moment of inertia of the object about the axis CD is you see here the xj is the perpendicular distance of the particle mj from the axis CD. I'm sorry, this is from not CD, from AB. Which passes through the center of mass of the object. And h, the h is the distance between the two axes AB and CD. And xj plus h, this is the perpendicular distance of the particle mj from the axis CD. Because CD is at a distance h from the axis AB. You see from this figure, you see this is AB axis, this is CD axis, and small h is the perpendicular distance between the two axes. So the moment of inertia I can be rewritten as this, and this one can be written as sorry, this is mg. But you see, this is nothing but the moment of inertia ig, and this will give you 0, and this is h square, and the sum of all the masses of all the particles, this is capital M. Proved. As I said before, these will be clear to you if you study carefully my notes that are uploaded in your Google Classroom. Okay, this is the end of this lecture.